Hi, this is the second video for chapter 27, and here we are talking about the magnetic field lines. And you need to know that we can do an experiment in the lab easily to to find how really these lines are really representing how really the force is really strong some points and maybe weaker at another point. We draw the lines so that the line through any point is tangent to the magnetic field at that point. We use like an actual situation in the lab. We have, this is the magnet. We're gonna put a compass, and the compass is gonna show the direction, which is from north to south, and we put the compass at different positions, and then we connect these. And field lines here, they don't actually intersect at all. They form also closed lines. As you can see, outside they are from north to south, and inside they are from south to north. I will say magnetic field lines point always away from the North Pole and towards the South Pole. At each point, if you want to find the direction of the field, it's the tangent to the line. The density of lines, they gonna represent the strong, like if it is very dense lines, then it's a very strong magnetic field. And when they are not dense, this is really weak field. Magnetic field lines are not lines of force. They are really magnetic field lines, and the force on a charged particle is not along the direction of the field line. Remember, we said that in order for us to represent or find what is really the direction of the force, we need to find the direction of the force using the right hand rule, where we are going to have B and V, they are going at the same plane, and then the force is going to be perpendicular to that direction, and we use the right hand rule as was described before. Also, we need to know that not only when I have a charge, a single charge, also when I have a straight line conductor that is carrying a current, we are going to find that there is really a field that if we have, like, we can have a field, like there is a field, of course, for a magnetic field for this conductor, but also to represent a field coming out of we use the notation, the dots for out. This is out of the page, and cross when they are really into the page. Okay, this is for the field. Also, I will say we know that the magnetic field of that wire is going to be concentric, circular like this, and then from one side they are going into the page, from the other side they are really leaving the page. Here also we need to know something about magnetic field lines of two permanent magnets. If I have two permanent magnets, we can also draw the field line for this. One important also concept, it is the magnetic flux, and for all the fields we actually calculate the flux, and the magnetic flux can be calculated by dividing any surface into small elements of area. We call it dA. One thing that here that I want you to know, that always whenever you have an area, the vector, which is the area vector, it's going to be perpendicular to the surface. And the magnetic flux we use for it, phi, is actually d phi, the magnetic flux is equals P perpendicular times dA. Now the total flux through the surface, it is the sum of all the contribution from all the individual area elements. And remember that the flux, actually it has the expression for flux, it is B dot A, and therefore is going to be A cosine theta, which is the angle between the two vectors. This is the dot product, and the magnetic flux, or the total, we can find it as B times cosine phi or cosine theta times dA. And whenever we're gonna have closed surface, then the total magnetic flux through any closed surface is gonna be 0, because the number of lines in equal the number of lines out. The SI unit of magnetic field, it is Tesla, and the Tesla, it is 1T, which is 1 Newton divided by ampere times meter. Another unit, which is the old unit, it is the Gauss, and 1 Gauss equals 10 to the negative 4 Teslas. The magnetic field of the Earth, it's in the order of 10 to the negative 4 Tesla, or 1 Gauss. The unit for the magnetic flux, theta B, is called the Weber, and the 1 Weber, it is Tesla times square meters. I'm gonna stop here, and then I'm gonna record another one.